Hello, class. These are our Calc 4-5 notes, integration by substitution. So we're going to be substituting today. So this is going to be a different technique that we're going to use when we have a composite function. So when we have a function inside another function. So think about something like y equals the quantity x squared plus 4x plus 3, all raised to the fourth power. So when I take a derivative, what I have to do is put the 4 in front. I am leaving my inside function alone, x squared plus 4x plus 3. This is chain rule. And I reduce my exponent, and then I multiply by the derivative of the inside function, which is going to be a 2x plus 4. So I have this outside function that I had to take a derivative of, and then I have to do a derivative of an inside function for chain rule. So now what we're going to be working on is looking at something like this y prime here and working backwards. And we're going to do that with substitution. So if we look at this integral right here, they're talking about if we have an f of g of x times g prime of x. So that's what we have right here, where we have f of g of x. So like this would be my g of x part, my inside function. And then this is the derivative of my inside function. This is this right here. And when I work backwards, basically this part is going away, right? Like I'm looking at integrating basically like this outside function, and I'm leaving that part alone. And then I have the plus c. And the way we're going to do this is with a u substitution. So instead of worrying about g of x, we're going to be letting u equal g of x. And that's going to be our inside function. So that's how we're going to make that substitution. So my strategy is always to look at a problem like example 1 and then find the function that looks like it's inside. So I would say that u is probably going to be this right here, the x squared plus 1. And if my u is x squared plus 1, then my derivative of u is going to be 2x. And normally we'd put this as a du dx over here, but I want my du to be by itself, so I'm going to multiply both sides by dx. I'm going to write the dx on this side. So now I just want to go through and make that substitution. So where I have the x squared plus 1, that's going to be my u, and it's being squared, so I'll make it u squared now. And then this 2x dx, all of that is going to be absorbed into the du. So now all I have to do is worry about integrating with respect to u. So this is just power rule. Increase our exponent to 3, divide by 3, plus c. And then the last step is really important. I do need to go back and substitute back in the x. So now I would have x squared plus 1 cubed, divide by 3. I have barely enough room here, and then plus a c. So looking at example 2, we first want to think about what looks like the inside function. So I can kind of see where the 5x looks like it's inside my cosine. So I'm going to let u equal 5x, and then du would just be 5 dx. And then I want to reorganize this. So I'm going to put this first. I'm going to write the cosine of 5x. And then this is going to be a 5 and a dx. I'm going to put those together now. I can multiply in any order. And now I can see that this is my derivative of the inside function. Derivative of 5x is a 5 dx. So this is going to be, that whole thing is my du. And this is going to be a u right here. So I'm going to have cosine of u du. That's all I have now. So that 5x is gone. So if I'm integrating cosine, and this is where maybe you go over here on your scratch paper and you say, well, how does that work if y equals sine x? Y prime is cosine x. So you're just like checking signs, right? So we're pretty good at knowing if we start with sine, when we take our derivative, it's positive cosine. So if I'm integrating and working backwards, now I'm going to have sine u plus c. It'll just be positive. And then I do want to make that substitution. It'll be sine of 5x plus c. So use substitution. Sometimes you can kind of look at something like this and you don't actually make the substitution. You just think in your head about what it would look like. But I'm going to show actually doing the use substitution today. All right, example 3 probably looks a little bit familiar. We're going to let u be our inside function again. And this time when I go to take a derivative, my du is 2x dx, but I don't have a 2 in here. So this example is just making us think, like, how do we force there to be a 2? So let's think about this. I know I want to reorganize it. I want to have the x squared plus 1 squared first, right? That's going to be my u squared part. And then I have this x dx, but I want there to be a 2 here. So if I want to multiply this by 2, I need to offset that by multiplying by a 1/2, because 1/2 times 2 makes 1. So now this line of work is equivalent to the line I have above, and now I'm going to make that u substitution. So this is going to be u squared, and then all of this right here is going to become my du. And now I can just go ahead and integrate. So I would have u cubed over 3 times 1/2 plus c. And then we want to substitute u back in. And let's see, that's going to be x squared plus 1 cubed all over 2 times 3 is 6 plus c. So again, we are doing these u substitutions, but then we do have to go back and bring them back to x again at the end. On the next one, it's really easy to see my inside function here is the 2x plus 1. Oh, it's minus 1. And so my du would just be 2 dx. So I don't have a 2 here. We'll have to do the same trick again. So I have square root of 2x minus 1. I'm going to multiply a 2 in, so I have 2 dx. If I'm multiplying by 2, I also need to multiply by a 1/2. And so now this is going to be my du. I'm going to have square root of u over here. So 1/2 square root of u du. And we might want to make that a 1/2 power instead. We tend to do better with exponents when we have fractional exponents instead of roots. I'm doing so many steps on this. This is really just a couple lines of work for this problem, but because it's brand new, I'm showing a lot of extra steps. I do need to add 1 to my exponent now. So that's going to be u to the 3/2 power, and I have to divide it by 3/2. So if I'm dividing by 3/2, I would really want to multiply by 2/3. So I'm going to have 1/2 times 2/3 times u to the 3/2. So that's going to equal 1/3 u to the 3/2. And then, oh, I'm forgetting my c, plus c, plus c, plus c. And then last step is to substitute x back in. So you can see like there was totally not enough room here for what this problem became, but we're showing a lot of extra work steps. And this was a 2x minus 1. I almost looked at the wrong problem. To the 3/2 power plus c. So there's our final answer. And again, you could do this with so much less work. So don't feel like you have to show 5 million steps right now like I am. So I think we're on example 5. Yeah, we just did 4. So this should be where we're at now. So on this one, I can see obviously right away again that 2x minus 1 is my inside function. So my du is 2 dx. Okay, looks straightforward. So let's go ahead and substitute. So I'm going to write square root of 2x minus 1. I need a 1/2 here. I have a 2 dx. There's just one problem. I have this factor of x here. So I can make a substitution here. I'm going to have square root of u. I can make a substitution here. That becomes my du. But what in the world do I do with this x? So let's go over here and do a little bit of scratch work. We need everything to be in terms of u. So if I have an x that I need to get rid of and I want to only have u's here, I need to look at the equation I have that involves both u and x. So that would be this equation right here. So I need to figure out what I could substitute for x. So I'm going to take this equation and I'm going to rearrange it and I'm going to get x by itself. And you can see like I'm going back to showing plus 1 on both sides. I'm showing all the work right now. And if I solve for x, I get u plus 1 divided by 2. So I'm going to substitute that into my problem for x. And I know you're thinking like, Miss Mullins, this does not look simpler. This does not look like a good idea, but I promise you it's going to work. All right, so let's see why. So I could go ahead now, and I do want to leave the 1/2 out here. But if I have a square root of u, that's really a u to the 1/2 power. And then I have times a u plus 1. And you know what? This 1/2 right here, I'm just going to multiply that in the front. We're going to make it a 1/4. in front of our integral. We'll just get all those fractions out of the way. And it might not still look simpler to you, but let's remember that if I have parentheses, I can go ahead and distribute. So this is much easier to handle than this problem we had at the top, where we had multiple terms inside our square root. We were really just kind of stuck. There was really no way to bring that x inside. There was no way to get rid of the square root. It was just kind of a mess. So when I distribute, 1/2 plus 1 would be u to the 3/2 power. U to the 1/2 times 1 is just u to the 1/2 to u for the whole thing. And now I can just integrate with power rule. So we're going to have a 1/4 out here. And then when I increase my power, it will now be 5/2. And instead of dividing by 5/2, I'm going to multiply by 2/5. And then this will be u to the 3/2. Instead of dividing by 3/2, I'm going to multiply by 2/3. And I'm going to leave my c outside because I don't want to mess with that until the very end. So now I'm going to multiply the 1/4. 1/4 times 2/5 would be a 1/10. So 1/10 instead of u, I'm going to make that substitution. U was 2x minus 1. I'm showing a little bit less work on this one because I'm running out of space. 1/4 times 2/3, same thing. The 2 and the 4 would reduce, and I would have a 1/6. And then we'll have 2x minus 1 to the 3/2, and then plus c. So there's a lot of different ways to handle the c. And so I know in class you were asking me, well, shouldn't I really have the c like this? But it's just a constant. It is just a number, and it is whatever number that makes it work. So to me, it makes more sense. If I have c here, then I have to distribute 1/4 to it. And then it's dumb to have a constant that's like a 1/4 c. It just should be a c. But that means this c is different than the c down here. And so to me, it seems like if I can just leave it outside and wait till the very end and kind of tack on that plus c, then I'm not changing the title of it over and over and over again. So you'll watch when we work in the next couple chapters, like this might be a C1, and then my constant in the very end is different, and that might be a C2, because sometimes I've had to distribute a 1/4 to them, or I've had to do something else to it, and the constants are a little bit different. So like they might get around it by putting a C1 here and then a C2 down here. And we really don't want to do that unless we absolutely have to. So the way I'm handling it here is just by kind of ignoring it and putting it at the end. And then I don't have to have multiple C's throughout the problem. It's just one constant. It doesn't matter if it's 1/4 C or just C. Either way, it's a constant. This is a simpler way to write it. So we would never write a 2 in front of our constant or a constant plus 4. We just want to leave that constant C. All of my constants together are just one number, right? It's all simplified down, and we're just leaving it as a C. So don't worry a lot about this at this point. So on this next one, I think this is a great problem for just kind of thinking through and maybe guessing wrong sometimes. So I'm going to make a wrong guess. First, I'm going to rewrite this, and I'm going to write sine of 3x, and then the whole thing is squared. And then I have cosine of 3x, and then I have dx. So it really looks right here like my inside function is 3x. So I'm going to write down that u equals 3x, but then my du is 3 dx. And when I go back and I make that substitution, I'm still going to have the sine of u. It's going to be squared. I'm going to have a cosine of u. My problem is I still have two functions that are being multiplied. So this is not going to work. It's not going to be something that I can find the antiderivative of. I need to go bigger with that u. So the next step is to think about, well, really the sine 3x, all of that is inside being squared. So let's go ahead and say that u is going to be the sine of 3x. If that's the case, then my du would be derivative of sine is cosine, and then times the derivative of the inside function, which is just 3. So I have like a chain rule here I have to do, and then I'm going to write a dx down. So let's look at how this would play out if I instead use this substitution. So that would mean I have u squared right here. This is a cosine 3x dx, so I'm missing that factor of 3. So let's go ahead and sneak a 3 in here. If I'm going to sneak a 3 in, I also have to sneak a 1/3. And really, I probably should have made that one more line of work. but realistically, we're going to run out of space. So all of this now is going to become my du. So I have u squared, and I have a du, and I have this fraction in front. So this is really just all power rule now when I am integrating. So when I'm integrating a squared quantity, it's going to become cubed. I have to divide by 3. I already have a 1/3 here. It's plus c. So that gives us a 1/9 u cubed plus c. And then my last step is to substitute u back in, and u was sine of 3x, and then I want to make it cubed. And really, we should be writing it this way. Oop, we're running out of space here. Sine cubed of 3x plus c. So if you had used this as your u substitution again, that would have given us sine of u squared cosine u du. Like it wasn't going to work. I still had multiple functions being multiplied together. I had no way to integrate that. So we had to go bigger with our u substitution. So sometimes you're going to make a guess and it's just not going to work. And that happens to me too. My notebook, my own personal notebook where I work out problems, is full of eraser marks. So we don't always do everything perfect. So example 7 is meant to be something that's a little bit easier again, where you can kind of go through and work it out on your own. So if you are watching this video for the first time, I would suggest just pausing it at this point and trying these on your own. But I'm going to go ahead and dig and do example 7 now. So my inside is here. So u equals 3x minus 1. My du is just going to be the derivative of 3x minus 1, which is 3 dx. So I can see right away on this, here's my 3 dx. So I have the 3x minus 1 to the 4th, and I have a 3 dx over here. So you probably don't even have to make the u substitution, right? I can see that this is all u being raised to the 4th power. Here's my du over here. So sometimes you make some notes underneath, but you don't really do that u substitution. So I need to take this part, raise to the 5th power, and divide by 5. So we're going to end up with 3x minus 1 to the 5th over 5 plus c. So this is often kind of the way I would do it on my own. I would make notes underneath. I would think about u, but I'm not actually integrating with you. I'm just going straight to an answer. So if that works for you, you are welcome to do that. If it does not work for you, then do the full-on u substitution, integrate with respect to u, and then put x back in at the end. Do it the long way like we have been. So on this one, you've got to decide which one is going to be u, which one's going to be u, my du. So we're always looking for the one that looks like when I look at this, it has a higher degree. And when I take the derivative of it, it just happens to be that first binomial. So we're going to let u equal x squared plus x. And then du is just 2x plus 1 dx. So that's set up just perfectly. So I could write this part first. And this is my u, this is my du. So it really comes down to this just being to the first power, right? I have u to the first power du. So this is the part I have to look at. And I know it feels like we're just ignoring this, and that's because of what happens if we go back to the very beginning. Remember, we started out with this one. We took our derivative, we ended up with that one. And if we're working backwards, because I got this by doing chain rule, by taking the derivative of the inside, when we're moving backwards and we're finding the original function, this is just going away. I know it's really kind of weird, but it does work. And if you want to integrate some of these and then practice going back and taking a derivative to convince yourself, that's fine. So I would need to raise this part to the 2nd power, divide by 2. So I'd have x squared plus x squared divided by 2 plus c. So again, this is kind of a shorter way to show work. Many are asking, should I have a divide by 2 or should I have a 1/2 in front? And I don't have any preference. A lot of times it's based on what I have room to show work for. So many times I find in my notebook I'm doing this one just because it takes up less space. So, but there's really no preference between the two. We're going to finish off example 7, and that's going to be the end of this video for tonight. So my inside function here is clearly the x cubed minus 2. So my du is going to be 3x squared dx. So let's just rearrange this. We have the square root of x cubed minus 2, 3x squared dx. So this is going to be like a square root of u. This is a du over here. All of that's going to go away when I integrate. So this is a 1/2 power. I would need to make it a 3/2 power. And then I would have to divide by 3/2, which is to multiply by 2/3. So like I said, just a couple of quick notes and you get your answer. So be careful about doing that. If you are not ready to take that step yet, you may certainly go through and show the work. But this is just giving you an example of how that could look when you're doing a little shortcut. Okay, this one does not look like we can have any kind of shortcut at all. So the first thing I'm going to do is I want to rewrite this so there's no fractions. Fractions are going to be difficult to integrate. So fortunately, I remember if I have a second power in my denominator, if I move that part up to the numerator or I take it out of the denominator, it's a negative 2 exponent. So I'm going to have a negative 4x times 1 minus 2x squared to the negative 2 power dx. And then I've got to figure out what is going to be my u. So this is the part of the function that obviously looks inside as a 1 minus 2x squared. I'm going to let that be my u. So then my du would be, well, the 1 will be gone when we take a derivative of a constant at 0. So I'll have a negative 4x dx. And that's exactly what I've got here. So let's rearrange. So 1 minus 2x squared to the negative 2 power. This is going to be like u to the negative 2 power. And then we have times negative 4x dx. So all of that would be my du. So when I integrate, I'm adding 1 to this exponent. So that means I'm going to be taking that 1 minus 2x squared. And when I take negative 2 plus 1, I don't get 3, I get negative 1. And then I would divide by negative 1 plus c. So anytime we have a negative exponent, I really like to do a fraction. And I think I'm going to put the negative 1 on top because it looks prettier to me that way. I could have the negative on the top or bottom, so I'll have 1 minus 2x squared. If this is first power in the denominator, I don't need to have parentheses or a 1 or anything. And then it's just plus c. Couple more problems. So let's look at this one. Where is my u? Well, let's remember, first of all, that this is the cosine of x, and then squared, and then sine x dx. So let's let u equal cosine x. And then our du would be a negative sine x dx. All right, so I need to add a negative in here. So if I want to multiply a negative in here, I'd have to multiply actually 2 negatives because 2 negatives make a positive. So we'll put a negative out in front. And then we have cosine x squared. And then we have a negative sine x dx. Okay, so this is going to be our du, and this is going to be u squared, and we have a negative out in front. So when we integrate, it's just going to be power rule again. So we're going to have to take this part here that's being squared and raise it to the 3rd power, divide by 3. Don't forget the negative, and then we have a plus c. And you could leave it this way, or, and again, I'm running out of space, so I'm just going to make it a negative 1/3 being multiplied in the front as a coefficient times cosine cubed x plus c. So you could certainly leave it this way. You could certainly leave it that way. Different ways to write these out. So we're looking at 2 here. We're not going to fully integrate. We're just going to think about strategy. So if we think about our u substitution, our u looks like it needs to be the inside function, which is going to be x squared plus 1. And then our du would be a 2x dx. So on this one, that works perfectly. I have an x, I have a dx, we're good to go. So all I have to do is manipulate it to get the 2. So I'd put a 1/2 in front. I have my integral. I would have x squared plus 1 squared, and then I'd have times a 2x dx. And I could do this now, right? This is my du. This is going to be a u squared. I have a 1/2. Maybe I'll just write this in a better, prettier format. So then you would just solve, right? But this second one, I can't do this u substitution. I have u equals x squared plus 1. I have du equals 2x dx, but I don't have that factor of x floating around and multiplying in there. So I need to have a different strategy. So let's think back to what we did before we had these fancy substitutions. Well, we can just expand it. And by expand, I mean take this quantity and actually square it. So if I am thinking about what happens to my first term, I would take this x squared and square it. So I'd have x to the fourth. My middle term in the trinomial would be my first and second doubled. So I multiply these two and double it. So that'll be a 2x squared. My last term will be the 1 squared, which is just 1, and that's dx. So these are both really easy to integrate now. So it's different ways to approach different problems. I could have also expanded here, but honestly, like, we'll make less mistakes doing a u substitution than we probably will with the expansion and then multiplying by x. So whenever you're adding more steps to a problem, you're adding more places that you can make a mistake. So I think this is exactly how I would approach either one of these problems. So I am going to take a break with this video for now, and I will do part 2 as soon as I can. Let me know if you need any help.